Okay, guys, so some of you asked for some additional questions to help lock in some of the learning from the RPO lesson. And so I've done that. I've created 10 questions that I'm going to model here in STK. And I'll ask you the question. You can just pause the video and then see if you can figure it out. And then just push play and you'll see the answer with some analysis. Before I do that, just wanted to lock in some of the learning from some of the conversations that I had over the past couple of days. So just for the scenario setup, here we have the geo. In the RIC frame that Reaper taught you, you can see I've got some altitudes denoted here just with some lines that'll make it a little easier for us to see what's going on. And I've got some degree spacing put on the geo belt as well. Okay, so let's just start with some of the basic stuff that you hopefully understand fundamentally now. If I do an Intrack burn of 2.84 meters per second, geo rule of thumb, that should give me 1 degree day per drift. So what I'm expecting is this is going to move to the left, up, and come to land at this point of 1 degree. So to make this easier on ourselves, I'm going to turn my time step to 2 hours. So it should take 12 clicks to represent 24 hours. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I did my 2.84 meters per second burn, which changed the altitude of my apogee, but fixed the altitude of my perigee at that same altitude. So I have to return to that same point in 24 hours. And you can see that I do that. Also visible from this display is that my apogee point is at 156 kilometers above the geo belt, and my perigee point is still at geo. Okay, what if I double the 2.84 meters per second? There it is. I go twice as far. Okay, but what did these actually do when I did these burns? 2.84 meters per second, it pushes my semi-major axis, which is the average distance from the Earth, the center of the Earth. It increased that value by 78 kilometers for the initial 2.84 meters per second burn. And that makes sense. What you'll see is with respect to this 78 kilometer point, I am traveling with it as though it were actually a satellite object. Let's do something interesting. Let's add another line that shows my relative motion with respect to this 78 kilometer line. Okay, so now what you're going to see as I push play is 2 lines emerge. One is that same line that is showing my 1 degree per day drifting NMC, and the other is my relative motion with respect to 78 kilometers. First question for you, what do you think this shape is going to look like? Okay, give you that pause time and let's see it. There you have it. It's an NMC, which makes sense based on the word. We've created a drifting NMC, but maybe this was something that wasn't as intuitive until you actually see it happen live. In that singular instant, we have created an NMC with respect to the new semi-major axis. And the reason we create that NMC is because we're not at the semi-major axis point at that time. And I think this will become more intuitive as we look at some other examples. But for now, let's just watch it one more time. We start out at geo and we're going to enter a drifting NMC. What are we drifting with respect towards? We're drifting with respect to our new semi-major axis, which is there at 78 kilometers. Okay, another thing we talked about today is the idea of energy in, energy out. And we talk about Intrack burns, we're adding energy into our orbit, and that is what pushes our semi-major axis higher. Or in the instance of a negative Intrack burn, would push it lower by a relatively symmetric amount between positive or negative. But what happens if we take that energy out? And does the timing of taking that energy out matter? Let's just run through that really quick. So what I'm going to do is I'm going to do 2.84 meters per second I'm going to wait 24 hours, and then I'm going to do a negative 2.84. And here you can see that happen, 2.84. I wait a day, and I do a negative 2.84. And now we're going to model that. First of all, before I show you the graphic, what do you think this is going to look like? Just take a second, think about it, and then push play. Okay, here we go. Yep, we've created a perch. And the reason why we created that perch is because when we got to this 1 degree point, we're back at our perigee, and we have taken all of the energy back out of the orbit, which means we took our semi-major axis and we put it back at the geobelt. 2.84 raises our semi-major axis to 78 kilometers. Negative 2.84 takes 78 kilometers out of our orbit, our semi-major axis's value, which means it is now effectively at the geobelt. But you might ask yourself, what happens if we were to do that exact same thing when we're out here at apogee? So as you remember from this motion, this is 12 hours to this point. So I'm just going to go ahead and I'm going to model that. Okay, so now we're burning 2.84, we're waiting 12 hours, and we're taking 2.84 out. What's this going to do? First of all, what's this going to do to our semi-major axis? And then secondly, what is this going to do to our east-west drift? Take a second, think about it, and then play the video. Okay, here we are at this point. And now what we've effectively said is our semi-major axis, we're going to take 78 kilometers out. Now, as you know, our semi-major axis is currently on this imaginary line. And if we take 78 kilometers out of our semi-major axis by a negative 2.84 meters per second burn, it's now on this imaginary line here. And physics is like, bro, you can't do that. You can't just have a semi-major axis and not be at your semi-major axis. Okay, I'm not going to let you drift anymore, but I also need to get you back to this same point in 24 hours. And what you're going to see is this Intrack object is going to now drift around its new semi-major axis. Let's watch it happen. Sure enough, we've created an NMC, stationary with respect to the geobelt. Okay, not bad, but what if we waited until later to do that 2.84 meters per second burn? What's the impact of that? Let's say we do it somewhere about here when we're crossing 78 kilometers, which was how many clicks? Let's see. Here's 12 hours, 13, 14, 15, 16, 17, 18. So what happens if we take all of our energy out of our orbit after 18 hours instead of at 12 or 24? What's our resulting shape going to look like now? Go ahead, pause the video, and let's take a look. Okay, here we are at that point. So once again, let's just focus on what the impact of the burn is. It pushed our semi-major axis to the geobelt. It took 78 kilometers out of our semi-major axis, which means we're no longer allowed to drift with respect to that line. And there's only one way for us to do that at our current point, and that's to go into an NMC. And this principle will remain true as we continue to progress through the orbit. So if we waited, let's say, 22 hours, the net result is still the same. We still are no longer allowed to drift with respect to the geobelt. So the end result is going to be an NMC. And the closer and closer you get to the geobelt, the smaller and smaller this resulting NMC is going to be. When you're way out here, the size of that NMC is a 156 by whatever 2 times 156 is NMC. It's essentially this whole shape here. When you're close to the geobelt, exact same burn, it's going to be a much smaller NMC. And that's because nature doesn't have to work very hard when you're almost already at the line that it wants you to be at to get you back to that line in 24 hours. So let's look at 23.5 hours. Even smaller. Let's look at 23.75 hours. Again, smaller and smaller NMCs. All of those are the exact same burn, but the timing of the burn matters. All right, let's look at what would happen if we did it after 3.28 hours. So very early on in the burn. And it shouldn't be surprising that it's just still going to be an NMC with respect to the geobelt. Okay, so that's all well and good, but let's start to apply this concept. So here I've got a object. So here I've got an object that is currently coincident with this 78 kilometer point, and it's on what you can see is a linear drift. So first question, what COEs are different between these two objects? It's the semi-major axis. And is eccentricity different? No, because we're seeing linear drift with respect to this geo point. Essentially, these are two relatively same eccentricity orbits. So, okay, what would happen if right now I took this object and I lowered its semi-major axis to geo? First of all, how would I do that? It's a 2.84 meters per second burn. Okay, so let's watch that happen. And it's important to remember this is going to be a negative burn, as I've denoted here, because before in the previous scenarios we've been raising the point of our semi-major axis. Now we're going to lower it. So the net result of lowering it, first of all, is this becomes our new point of apogee. It does not change. When you do a negative burn, you're setting your point of apogee. When you do a positive burn, you're setting your point of perigee. So let's just watch what happens. First of all, what do you think is going to happen? Hopefully you paused the video and thought about it yourself. But sure enough, what we've said is at this instant in time, this Intrack 3 satellite that is at 78 kilometers is no longer allowed to east-west drift over 24 hours or one period with respect to this object. There's only one type of orbit that does that, and it's going to be an NMC. Okay, so you're probably saying, Ace, that's way too easy. Give me something a little more challenging. All right, so we're looking at fundamental principles here. Next, what I want to do is, what if I have the burn from 2.84, let's make it 1.42. What is that resulting shape going to look like? So now I'm doing a burn of negative 1.42 at that same point in space. Take a second, think about what this is going to look like. Okay, so what was the result of us doing that semi-major axis lower? We've lowered our semi-major axis now to 39 kilometers above the geobelt. But we haven't changed our point of apogee. It's still going to be at 78. So now the relative distance between our semi-major axis and our point of apogee is 78, or 39 kilometers, which means that we're going to see that our point of perigee is at the geobelt. So let's go ahead and push play and watch this happen. Sure enough, we are now in a drifting NMC, and we're not drifting at 1 degree per day anymore, which we'll be able to see here. We're now drifting at half a degree per day. And you can tell that from this point of apogee is here at geo, and now our new point of apogee is about halfway between 1 degree and geo. And if you remember from one of the early scenarios I showed you, if we were to draw a line of what does our shape look like with respect to 39 kilometers, sure enough, it will be an NMC, which is this drifting NMC as viewed from the altitude of 39 kilometers. Cool stuff. Okay, but now you're probably thinking, but Ace, that's still way too easy. What if I want to do an NMC around this object down here that's drifting and has a different semi-major axis than geo. How would I do that? Okay, so essentially what you're asking to do is to change your current semi-major axis to this object's semi-major axis, which is going to require what type of burn? Well, you should be able to see that this semi-major axis is geo plus 78. This semi-major axis is geo plus minus 78. So the relative distance between these two altitudes is 156 kilometers. So if I want to lower my semi-major axis by 156 kilometers, all I have to do is do a 2.84 meters per second burn times 2, which is 5.68 meters per second, negative intrack. Let's watch it happen. Okay, here we go. First of all, what do you think this shape is going to look like? Well, there's a few things we know. We know that our new semi-major axis after that burn is on this imaginary line. And we know that our point of apogee, our altitude of apogee, hasn't changed. So it's always going to be along this line. So the distance from our point of apogee to our semi-major axis is 156 kilometers, which means that our new point of perigee will be 156 kilometers below this point here, which will be somewhere at 234, negative 234 kilometers, if I did my math right. So here we go, let's watch. Sure enough, we've created this dramatic drifting NMC to the east. And you can see that our apogee is still at the same altitude that we started at, 78 kilometers, and our perigee is well below that. And we're drifting around a line along this satellite objects line. So let's just view this NMC with respect to this satellite line. Okay, so here we go. What do you think this is going to look like? You're going to see two lines. One is with respect to geo, and one is with respect to that object drifting. Look at that beautiful NMC. So by now you're probably getting kind of bored of in-track burns and you want to shake it up with something a little more interesting. So, okay, first of all, let's start with a radial burn. Got a radial burn here, and it's currently 5 meters per second. So what's this going to look like? Sure enough, it's going to be an NMC. Okay, so that's 5. What if I do 10? What's that going to look like? Essentially double the size. What if I do 20? Okay, what if I add a 30? Looks like about 3 times the 10 and 6 times the 5. Okay, so these are essentially scaling appropriately. What is important to note, though, is none of them are creating east-west drift, you know, within a certain amount of tolerance, just based on the fact that these are non-inertial reference frames. Radial burns do not fundamentally create linear drift because they don't change the semi-major axis of your orbit. So that's cool, I guess, but what else can we learn about radial motion? All right, let's start with the NMC test case. I've got an object that is currently in an NMC, and I want to do some radial burns. And what is going to be the impact of those radial burns? So let's just start with the case that we are at our point closest to the Earth or our perigee. What happens if we do a radial burn of any magnitude at this time? Go ahead and think about it, and then I'm going to show you. Now, it might not be super intuitive of what this is going to do, but stick with me. You've added some faster motion in the radial direction. So this is the radial direction, and you're adding velocity into the radial direction. So if you kind of think of this like a ball that you're throwing up in the air from the Earth, you're essentially trying to throw it higher now because you're giving it more velocity. And so what I would expect to see is you're going to see this radial object move to a higher point of apogee. So let's go and see what happens. So definitely we beat our old point of apogee. We haven't changed our semi-major axis. But what's really interesting about this is because we've increased our point of apogee, but we haven't changed our semi-major axis, and the point of apogee and the point of perigee are symmetric around that semi-major axis, we also had to lower our point. So as we come around to this point of current perigee for our original orbit before the burn, and we're saying I've added extra velocity up away from the Earth, so that I'm going to reach a new higher apogee. Two things we know have to remain true based on what we talked about. We know that nature needs to get us back to this point in 24 hours. And the reason why is if it doesn't, we have now violated the principle of what semi-major axis means. Semi-major axis is setting our period, and the only way we can have a periodic motion is if we return to the same point in space with respect to our current line in 24 hours. So you're going to see that we could do that, but we also know this can't be our new point of perigee, because if our apogee is higher and this is our current lowest point or closest point to the Earth, the new one has to be somewhere down here. So that's what's causing this apparent motion over to the east, to the west, excuse me. So true to physics, we do return to our same point where we conducted the burn. Okay, so what if we wait another 6 hours and then we do this burn here as we're ascending or crossing through the geo line, as we're crossing the geosynchronous altitude. Okay, what do you think is going to happen here if I do a burn positive radial when I get to this point? Once again, we've increased our point of apogee and lowered our point of perigee. Cool. But what if instead, when I got to this point 24 hours ago, I did a negative radial burn? So you can see that currently my motion is away from the Earth. So what if I were to conduct motion to push me closer back to the Earth? What do you think you're going to see with this? Okay, so now I've just switched the sign. What do you think you're going to see? Think about it. Okay, here we go. Essentially what we're saying is we're fighting our velocity that's carrying us out to our current apogee. So we've lowered our apogee and we've lowered our perigee. So what's really interesting about radial motion, at least for me, is that this is all based upon your radial velocity at a current time. So because we did this negative burn while we were moving towards our apogee, our radial motion, our radial velocity was positive. And so we did a negative and we made it less positive, which made a smaller resulting NMC. But if we wait another 12 hours, so we get rid of this. So if we wait another 12 hours, instead of burning here, we burn here. Now what do you think the impact of a negative velocity burn is going to be with respect to the shape that you see after? Think about it and let's model it. Okay, here we go. Place your bets. So yeah, it's exactly the same shape that we saw from before when we did the positive radial 15 on this side. Only now, because our radial velocity is negative, we've made it more negative, which means we've pushed our point of perigee lower and we've raised our point of apogee. All right, one last thing that I kind of want to show you guys is, I guess you could call it a challenge. So I've got two ACE's good ideas. And let's look at what they're doing. They're starting here at this point of geo. And let's look at the orbit. So let's look at idea number 1. It's got a maneuver that is 10 radial and 2.84 Intrack. It propagates for 24 hours, and then it does a negative 2.84 Intrack. The next one for idea 2 is starts in that same location, and it just does a 10 meters per second radial burn. And nothing else, just 10 meters per second. All right, so idea 2 is just 10 meters per second. Idea 1 is a combination of 10 meters per second and 2.84 meters per second simultaneously in a single burn. And then when it gets 24 hours later, it does a negative 2.84. Nothing related to radial. My challenge to you guys when you get back from your trip is to tell me, what do these resulting shapes look like? And then we'll talk about what the real important factor is there, but I want you guys to think about that for a second. And yeah, just draw them out, model them out, do whatever you can do, and then let's talk about them when you get back.